Welcome back. Today we are going to start our lecture number 30. So we are discussing the fluorescence anisotropy, and we are done till the Perrin equation. So what is Perrin equation? Let me write it once again. So Perrin equation is written as R0 by RSS equal to 1 plus tau f divided by tau OR. So where this R0 value is initial anisotropy, RSS my steady state anisotropy, and this tau f is my fluorescence lifetime, and tau OR is orientational relaxation time. So from here what you can see is that without, if you have some idea about this value of R0, right, and this RSS can be measured very easily from this fluorimeter where you have this polarizer and analyzer. Right. Normal fluorimeter does not have this polarizer analyzer, but if you can install a polarizer analyzer so that their excitation light is polarized light and the emission you are going to analyze which is the perpendicular direction and which is what is the intensity of the perpendicular direction and what is the intensity of the parallel direction, then you will be able to calculate this R steady state easily. Right. And if you have this knowledge of this fluorescence lifetime, then you will be able to calculate this tau OR. Now, if you recall that our Stokes-Einstein relationship, then this tau OR can be written as tau OR equal to eta v by RT. Right? This is my Stokes-Einstein relationship, where this eta is equal to the viscosity of the medium V is molecular volume and R is my universal gas constant and T is my absolute temperature. Now, if I plug in this expression for this tau OR in the Perrin equation, what we will going to see is the following: 1 over R S S equal to 1 over R 0 plus tau f into R divided by R 0 into V into temperature by viscosity. Right? It means that now if I plot, this is the measurable quantity, this is your measurable quantity, this is the property at a particular temperature, obviously you know the viscosity, so then T by eta is a known quantity, and I can measure this R steady state for a different value of T by eta. I change the temperature, obviously viscosity will change, so T by eta will change, and for a different values of this T by eta I can measure this steady state anisotropy, and then I can plot it. Right? So let us plot that same. So if I plot, what we are going to see is 1 over R steady state versus T by eta. You are going to see a straight line, and intercept will be equal to 1 over R 0. So from here you will get some idea of this R 0, right? And then slope will be equal to tau f R by R 0 V. Now if tau f, the fluorescence lifetime, is known, R obviously is a constant, and R 0, if you have a prior idea of this R 0, then you can calculate V, that is the volume, and this is a well used equation in application of the fluorescence anisotropy. So, from with this you can actually determine the size of, let's say you are working with a protein and this protein is getting denatured. Once the protein is getting denatured, the size will increase, and if you have one fluorophore already attached to the protein, then by measuring the fluorescence anisotropy, that means the fluorescence this RSS value, by measuring this RSS value, what we will be able to do, we will be able to see that at this particular condition what is the volume of the protein, that means the size of the protein and so on. Right? Now, one of the important thing here is that what will be the value of R0, right? That's the biggest question, right? So, that should be measured, otherwise I cannot say anything about this. And we have seen that limiting value of R0, you remember our first equation, I have written R equal to I parallel minus I perpendicular divided by I parallel plus twice I perpendicular. Right now I am not talking of, I am not including this G, because considering that G equal to 1, if G is there then just a factor will be there, right. So, consider that G value is equal to 1 and I am now doing all those things. Now, in case of time dependence, then this is nothing but RT is equal to I parallel T minus I perpendicular T and so on. So, that means at time t equal to 0, that is my initial anisotropy R0, and that is whatever I have written here as R0. So, in this case I have to determine what will be the value from that particular equation. When I said that it is I parallel minus I perpendicular divided by I parallel plus twice I perpendicular, obviously at time t equal to 0 there was no emission from this perpendicular component and there is only emission from this parallel component, makes it R0 equal to 1. But whether this is true, and I also said that when this R value will change as time goes, because the intensity of the perpendicular component will increase and parallel component will decrease because of the reorientations of the molecules or transition dipoles when at the excited state. So, as time goes there will be the intensity of the parallel and perpendicular components will be equal, and in that case you will see that R will going to be 0 ultimately at after a certain time. Now, let us see these things, right, in a more detailed way. So, let us now consider that you have excited the molecules along z axis. So, z axis is your polarization for the excitation light. Okay? So, let me write here. So, polarization of the excitation light is along z. I consider it over here. So, if I consider that only those molecules, that is why I said that only the molecule whose transition moments are along the z axis, they will be preferentially excited. That is what I said earlier. Again I am telling the same thing. So, those molecules will be excited, and if the direction of the absorption transition moment and emission transition moments are same, like they are collinear, then the emission will be also along z axis. That is my condition now I am imposing. Here the direction of the absorption transition moment and emission transition moment, they are collinear, then the emission will be also along the z axis. Take a note on that. Okay. Now, let me tell you that now the molecule has been rotated at an angle theta, right, and now I am looking at this molecule. So, now this bold arrow is my molecule which has been rotated at an angle theta from the direction of the excitation, and now I am looking at this molecule. So, here you see the rotation of the molecule makes a component of this I parallel as cosine theta, as you know, and but the molecule can rotate, like if this is my z axis, the molecule can rotate from here to this side as well as from here to this side. In all the cases the angle is theta. This side angle is theta, this side angle is theta. That means I need to worry about all these different angles for a fixed value of theta. That means, if I assign this angle as phi, then the value of phi should be 0 to 2 pi. That is what I have written over here. So, now here you see for this perpendicular component, this should be sin theta sin phi, correct. So, the intensity, those are the electric fields. So, intensity I parallel will be equal to cos square theta and I perpendicular will be sin square theta sin square phi. But here also please note that we should take all values of sin square phi. That means, I should take the sin square phi average, right. So, I should take the sin square phi average. So, let me find out that. So, sin square phi average is equal to integration 0 to 2 pi sin square phi d phi divided by integration 0 to 2 pi d phi. So, and I already got this I parallel equal to like this, I perpendicular is like this. So, if I can calculate this, I can simply replace this sin square phi with this. This I can do, as I said, because that all values between of phi between 0 to 2 pi will have the equal probability. So, now I can evaluate this integration 0 to 2 pi sin square phi d phi, right, that part. So, if you integrate this, then you will get phi by 2 minus 1 over 4 sin square phi, limit I will put 0 to 2 pi divided by this will going to, this is simple, this is just 2 pi. So, then this will going to be pi by 2 pi is equal to half. So, as I got the sin square phi average is half. So, I will simply write I parallel is equal to cosine square theta and I perpendicular equal to half sin square theta. You see that this is now half sin square theta. Now, R is equal to I parallel minus I perpendicular divided I parallel plus twice I perpendicular, which will going to give me cos square theta minus half sin square theta divided by cosine square theta plus 2 half and 2 this will cancel sin square theta. So, this is equal to 3, and then I will just simplify this, and what you will get is cosine square theta minus 1 divided by 2. Now, as you can see here that for the value of theta, if the theta equal to 0, right, the theta value could be anything, right. So, let me put first theta equal to 0. That means, it has not oriented because you have excited along the z axis, and just immediately after excitation you are looking at the r value, right. So, theta equal to 0. So, for theta equal to 0, this is nothing but 3 minus 1 divided by 2. So, this is equal to 1. For theta equal to 0, the value of r equal to 1. So, here I got the initial anisotropy is 1, right. And now, as the molecule will rotate, the theta will change, theta will increase, and it will increase, and ultimately at some value of theta, the anisotropy will be 0. So, when the cos square theta equal to 1 by 3, as you can see from this equation, that when cos square, okay, let me write these things, this is important. So, when for theta equal to 0, r I got equal to 1, and when theta equal to 54.75 degree, it means cos square theta equal to 1/3. What you get? You get r equal to 0, right. That means the molecule is not necessarily has to reorient itself 90 degree to make the anisotropy equal to 0. Only 54.7 degree orientations will make the anisotropy equal to 0. Now, whatever I said here, right, is an ideal situation. That means that your excitation light is polarized along z axis. Only the molecules whose transition moment, absorption transition moment is oriented along z axis, only those will going to be excited like that. Now, now these molecules will reorient themselves and the theta value will change. I consider that the direction of the absorption transition and emission transitions are collinear. So, the emission will also come along that line, right, as I have excited, and then I got this equation. However, it is not true that once you use a vertically polarized light or light electric field is oscillating along the z axis, that will only excite the molecules which are oriented along the z direction. Obviously, there will be some component of even the electric field is like this and the molecule is like this. The component which is along this direction, the component of the electric field which is along this direction, that will also be used to excite the molecule little bit. It is true that those molecules which are oriented just perpendicular to the direction of the electric field of the excitation light, those will not be excited at all, that is true. But there is a possibility that the molecules which are oriented at a certain angle from the collinear geometry of compared to the excitation polarization, there will be some possibility of the excitation, and that is known as the excitation photoselection of the chromophore. Let me discuss these things over here. So, see, this is the excitation photoselection of fluorophore. This is what I said. The molecules which are oriented like this way, they will be excited, that is sure, but the molecules which are oriented like this way, they will also some chance for the excitation, right, that is what I said, and that is proportional to the cos square theta if the molecule is oriented at an angle theta from the polarization of the excitation light, right. So, that will be proportional to cosine square theta. Okay, so let me write this over here. So, as you use, okay, let me write it like this way. So, the excited state population will be distributed symmetrically around z axis in this particular case. Okay. So, that distribution, right, I can write this as f theta d theta, that is possible to show that this is equal to cosine square theta sin theta d theta. Right. So, and this anisotropy is given by, I have already seen, 3 cosine square theta minus 1 by 2, right, that is what I already got. So, in this case what I will do, let us continue. So, in this case that cosine square theta, right, not here, in this case that cosine square theta in my earlier equation is that value of theta is not a single value, because now the theta value is different, and that is my distribution over here, what I said. This is distributed. So, when a molecule, and each molecule will make a different angle theta, and for a different theta value, all the phi values are possible. Right? So, this is a like a complicated situation, and in this case I should not write the equation as cos square theta, but I should write the average cos square theta. So, then I have to take the average cos square theta, right. So, for this average cos square theta, what I will write, average cos square theta equal to cos square theta f theta, because this is my distribution, f theta d theta is my distribution, and that integration from 0 to pi by 2 divided by 0 to pi by 2 f theta d theta. And if you evaluate this, this is integration 0 to pi by 2 cosine to the power 4 theta sin theta d theta divided by 0 to pi by 2 cos square theta sin theta d theta. So, if you evaluate, you will see that this value is 3 by 5, right. So, all this theta, what is the distribution of theta, is because of the excitation photoselection, and this distribution is because of the excitation photoselection, this is my initial value of the cos square theta average. So, now if I put this cos square theta average in my original equation, let us see that r equal to 3 cos square theta, but now this is average because I have so many things, minus 1 divided by 2. So, then this is equal to, for the initial value, 3 into 3 by 5 minus 1 by 2, this is nothing but 0.4. So, R0, what I will get is a 0.4, and this is true for when the absorption and emission transition moments are collinear with each other. If they are not, then this value will not like that. If not, if the absorption and emission transition moments will make an angle beta in between them, right, then this R0 equation, right, now I am writing R0, I am not writing R right now. So, R0 can be written as 2 by 5 to 3 cosine square beta divided by, say, minus 1 by 2, right. So, when this beta equal to 0, that means they are collinear, right. Immediately what you are going to see is that R0 equal to 0.5. If beta equal to 54.75, then what you will immediately get that R0 equal to 0. If beta equal to 90 degree, that means if this absorption and emissions are perpendicular to each other, right, then for example, let me give you example that will then it will be much clear to you. Let us say I have this molecule, our famous example, many times I use this molecule, anthracene, right, and I told you this absorption for the S0 S1 is along this direction and S0 S2 is along this direction. I consider that emission is also the same, but if you now excite from S0 S2, and but you will get the emission from S0 S1, from S1 to S0 because of the Cauchy's rule. So, you are exciting along this direction. So, here this direction is your excitation, because you are exciting from S0 to S2, but emission is along this direction, is different, right. So, they are perpendicular to each other. Now, if you excite, emission is from S1 to S0. Now, if you excite from S0 to S1 and then S1 to S0, then they are collinear to each other, right, then they are collinear. So, in that case, that is the value, beta value is equal to 0, and in this case the beta value is equal to 90 degree. So, for beta value equal to 90 degree, what we will get is this R0 value equal to minus 0.2. So, what you can see is that the value of R0 or initial anisotropy or fundamental anisotropy, right, it depends on many factors, right. Many factors means basically this is what is the angle between the absorption transition moment and the emission transition moment, right. So, for a different molecules, this angle will be different, so the value will be different. So, this has to be measured, and we can measure it by time resolved anisotropy decay. As I told you, if you have a very high time resolution like a femtosecond time resolution using the fluorescence upconversion system, then by putting this polarizer in the femtosecond upconversion system either at the parallel or in the perpendicular position compared to the direction of the excitation or polarization of the excitation laser beam, you will be able to find out the value of R at a very early time with a very high time resolution, and that will going to be your R0 value, right. Okay, so this all about this fluorescence anisotropy, and as we have little more time, then I think that we should continue our discussion on little more advanced topic of this fluorescence anisotropy, which is the associated anisotropy decay. Associated anisotropy decay. So, right now what I said is that the decay or anisotropy decay of a fluorophore present in a particular media, right, in a homogeneous media. Now, I am thinking of that if I have two fluorophores, right, but present together in a solution, but their environment are different. The environment of two different types of fluorophores are different, but they will going to give the contribution to the anisotropy decay. Then what will be the effect? So, let us take this as that I have I of the ith component is defined as alpha I. So, this is my lifetime part, right, T by tau f I, and my RT part RIT is equal to R0 I into e to the power minus T by tau over I, right. So, I can write the fractional intensity of the ith component. If it is only 2, then first or second component at any time t, just I write this as FIT equal to alpha I e to the power minus T by tau f I divided by sum over I alpha I e to the power minus T by tau f I. That means the time dependent anisotropy, that RT should be given by sum over I, because if it has more weightage the early time, then the more weightage of the RIT will be there, because it is now more weightage, and in the later time. So, I can simply write RT equal to sum over I FIT RIT. So, you see it is a complicated thing, right, and as expected the anisotropy will also be complicated. Usually anisotropy looks like that it started from some value R0 and exponentially decay, but in this case if you see this anisotropy decay, it will look something like this. But using such kind of formula, you can analyze it without any problem. So, if I now plot R t as a function of t over here, then it could looks like this, or it could looks like this. So, it does not looks like is anisotropy, but this is because of this two different fluoropores, two or more different fluoropores present whose environments are quite different. One quick example is that the tryptophan, right. So, if you have tryptophan in a protein, right, when tryptophan is present in the protein, the RT value, right, or this tau R value is very large because the protein is very large. But if it is now free, right, then the tau R value is really small and the lifetime is also quite different. So, for such kind of complicated cases, what you will going to see such kind of associated anisotropy decay, and you need to really careful, you have to be really careful for the analysis of such kind of anisotropy decay. Okay, so, we will finish here and thank you for your kind attention.